that relates chemistry, structure of local bonding, chemistry to magnetism. Without any theory, you can get a lot of magnetism. My understanding it works that nicely, not for S electrons, D electrons. D electrons are extended objects. They always run around. Even in multi-insulator, they make incursions neighborhood, forming covalent bonds. Some people say molecular orbitals, whatever. So the transition level compounds are basically close to metal insulator transition on this side, on this side. U and bandwidth, 2-3 electron volt, gaps are much smaller usually. So it's a kind of, we are borderline being, it's covalent bonding. So this implies that magnetic energy is actually a fraction of chemical bonding energy, covalency energy. So to understand magnetism, we have to first look at how electrons make bondings, form orbitals, this is following the orbital line, and then we get magnetism automatically. So we try to optimize LDA plus U does it automatically. So it knows band structure, hopping, etc. By hand, we calculate, we try to optimize orbital structure and spin structure that, we get most of, kinetic energy, virtual kinetic energy optimized. So when we do that, we encounter three basic forces, ground forces in our small life that transitional compounds, orbitals and spins. There are some three limits. Orbitals couple strongly, weakly to lattice. They become part of the lattice actually, forming phonons or vibrons, etc. You may start sample. You may have sample. All three interactions are competing, highly frustrated. Because of that, eventually at low temperature, sample will move either this direction or that direction. So it's a phase transition somewhere. So if we come to this limit, system still highly frustrated because of orbital and spins. They, chemical bonds are not really that rigid like in this limit. We are dangling, changing the color, bonding, anti-bonding, non-bonding orbitals. This is Kugelhamsky physics, complicated physics. When we have lambda spin-orbit coupling, it's substantial. Of course, this reduces the Hilbert space a little bit because of binding spins to orbitals together in forming J moments like in the Earth, but because of, you remember, covalency, F is really localized. Physics is very different. And this corner, people called, I think that this guy coined the notion of spin-orbit coupled multi-insulator. So this insulator still will remember coupling to the orbital, have a lattice, because orbital is part of this J moment. So it's usually samples coming here, they have, large magnetoelastic coupling. So actually orbital transition, Young-Taylor transitions become pneumatic transition, things like that. And these samples also will remember Kugelhamsky spin frustration, spin orbital frustration, because this, spin Hamilton in this corner is just projected the same Kugelhamsky Hamiltonian. So it's now I'm talking about spin orbits called magnets. We have plenty of them. This gentleman left, lots of phase space in Hubbard models. We anticipate there will be many materials following this regime, different from very small Couperay area. So now I just throw a few examples of, still space is not enough. I put some. They may show already optical or the magnetic indicator model. It's particularly interesting case. Every car you have fire into about that issue. So this is spin-orbit coupled material. You see that we have many, there will be many examples. People have, who study these materials and then advance their physics. They are basically in the audience. They know the, excitement. So at this point, I just wanted to mention one name, Georgia Kelly, not to get extra time, just because, I am not that it's fine. Just to acknowledge and thank him in public that for great excellent collaboration over the years. George, thank you, George. So these other names will appear in course. Spin-orbit multi-insulators, we take one ion, in the air, diagonalize quickly, and realize that actually the spin-orbital Hilbert state for an ion, it actually contains a lot of multiplets. We look at this low ground state, we realize it has some 4-fold degeneracy, 5-fold degeneracy, no degeneracy, and assign them Hilbert spin. It's just object, spin algebra. The physical meaning is completely different. So many ions, people start with this spin. Spin 1/2, of course, is special because it's quantum, two-dimensional, operators, all that I will mention. And also, interesting thing that there's no spin at all, but there is some another virtual spin nearby. We can activate that. So in that case, Hilbert state, I will take this. See, it's non-interesting thing. We have to, and then you get multiple. Of course, spin mimetics, all that over. Physics of J is different from S. To illustrate that, so imagine you have one P2G hole, so this is, you have three P2G triplets. So the Young-Taylor coupling, if you go on the triangular upstairs, you will see that you have real wave function and in complete sequence, spin 1/2, G factor 2, this is spin population. Now, if I take the same whole, remove the degeneracy, look at the J1/2 state, I have again Kramer's degeneracy, effective spin 1/2, but wave function, as Naoto said in the morning, is complex, it's a unity, this imaginary. That makes shape very much different, you see. So just this guy makes sense. It's interesting. And then also spins entangled. So anyway, so this requirements doublet is made actually basically mostly of angular momentum L, because L is 1, this is smaller. So essentially we are talking about orbital magnetism in this material. Okay? And this magnetism has G factor -2. And the magnetic field, it will align different parameters. But formally, for mathematics, it's spin 1/2. And this, gives, enormous, kind of difference when you look at physical, stuff, starting with, Young-Taylor stuff on Hilbert stuff. So triangular lattice, kind of frostbite, canonical example. If you have, 120 nice Heisenberg interaction. If you take this kind of Kramer's doublet, put it on triangular lattice, you realize, so it's Heisenberg plus some bond dependence. Bond dependence, kind of course, if you have spin-orbit coupling, you get Ising-like anisotropy along it. It's kind of symmetry. But now if you have high symmetry crystal, bonds are rotating C4 symmetry, C3 symmetry. So Ising axis, easy axis must rotate. It should. And then they analyze kind of spin wave. You get this unit cell. It contains spin vortex, and then